Osmotic pressure happens from osmosis. So in osmosis, the idea is that you've got two concentrations. You can see on the left side, this concentration here is a lot, down here, is a lot less concentrated than on this side. You can just glance at that and you can immediately see. But they are separated by a little tiny membrane that lets something pass between them. So the instinct is to say, well, if they want to have the same concentration, why don't we just take some of these particles and put them over here, and that'll give it the same concentration. Well, it would be fine if that was possible, but the semi-permeable membrane, the little spacing between them, it's too small. So they can't get through, the particles can't, but the solvent, the water can. So what happens is that a certain amount of the water moves over to this side. And you can kind of blur your eyes a little if you need to kind of tell that the left side now has about the same spacing as the right side. So that's osmosis. And you can learn all about that in biology, not in chemistry. Chemistry, though, does want you to know that when you have solutions like this, that there's a pressure created moving across that membrane. And the pressure, you can do things with that pressure. We aren't going to go a lot into what they're doing. This is probably one of the few times in the entire course you'll hear about osmotic pressure, but you'll hear about in biology even more. So let's look at if you have a solution of a non-electrolyte in water. And here's the molarity. And it's weird to me that they're using an M to represent molarity, because don't we have enough M's in chemistry? Molar mass, moles, like enough M's, right? So I don't know why we didn't call this concentration times R times T, but maybe we just have plenty of C's also. But this is molarity times R times T. Now, this pressure, it falls in the same section as like gas pressure. So look, if we rewrite the M, the big M, as moles per volume, RT, and then we move the V over to the other side, that should look fairly familiar to you. PV equals nRT. So this is not a new equation. We're just putting the N and the V together, and we're calling it molarity. So again, not a new equation, but since we're doing that and it kind of is really close to or comes from the gas equation, we need to use the gas R constant. Whenever you're dealing with thermodynamics, you want to use that 8.3 constant, but when you're using gas type things, you want to use that 0.0821 constant. So let's go ahead and solve the problem. This is mostly plug and chug. There's not a lot of weird tricks to these, I guess, unless you have something in the wrong unit to begin with. You know, maybe you have to convert like a percent mass into molarity or something like this. But this is a molarity problem. You'll notice in the section about change of temperature and freezing point depression, that's a molality concentration. Now this one was made with molarity concentration. But we're just going to plug it in, so we have our 0.37 molarity times 0.0821 liters ATM moles Kelvin, and times your temperature. It's saying it's 37, but like everything else in the gas world, you're going to be basing your units on the unit of the constant. So our molarity units here, remember this was moles per liter. So see, our moles cancel and our liters cancel. Our ATM is a pressure unit, so that's what he's going to come out in. And look, our T is in Kelvin. So this needs to be 37 plus 273.15. And I just put it like that. I think it's a little bit of a waste to calculate the temperature multiple times. Just put it on your calculator all at once. 0.37 times 0.0821 times parentheses 37 plus 273.15. And so then that gives us that the pressure is 9.4. Looked like we had 2 sig figs. And then again, the unit that remains, if this is Kelvin, is ATMs. So use your constant. Make sure you use the right constant, right? But use the constant to tell you the units that everything else should be in. That's 9.4.